When the Hubble Space Telescope turned its attention toward 3IATLAS on November 30th, astronomers expected another routine snapshot of a faint interstellar visitor. Instead, they obtained a remarkably clean and detailed benchmark image. That now serves as the foundation for every ongoing interpretation of this object's behavior. Hubble's Wide Field Camera 3 captured the comet from a distance of about 286 million kilometers, tracking its motion perfectly during the exposure. Because the spacecraft followed the object across the sky, the background stars stretched into streaks while the comet's nucleus stayed crisp, forming a compact central brightening wrapped in a thin, ghost-like haze. The shape of that haze, the coma, revealed a subtle but meaningful asymmetry. A slight extension toward the Sun, a faint sunward protrusion that has stirred both scientific discussion and public curiosity. Some observers quickly labeled it an antitail, a feature that, despite its unusual phrasing, has entirely natural explanations rooted in dust dynamics and observational geometry. From a technical perspective, Hubble's newest image provides astronomers with an extremely valuable constraint. Ground-based telescopes have been monitoring 3IATLAs for months, but atmospheric interference and variable seeing conditions limit their ability to separate the comet's core structure from noise. Hubble, however, resolves fine details in the coma's brightness profile that Earth-based instruments can only approximate. These measurements allow modelers to compare predictions. Are we looking at directed jets propelled by sublimating gas, cluster of small fragments, or simply normal dust grains, pushed and sorted by solar radiation pressure? The November 30th data does not answer these questions outright, but it sharply narrows the domain of plausible explanations, a critical step in scientific analysis. Across the globe, astronomers continue a coordinated monitoring campaign spearheaded by both space agencies and national observatories. Facilities in Chile, Hawaii, Australia, and Europe track the comet across multiple wavelengths, gathering brightness curves, spectral data, and high-resolution optical frames as the object changes position relative to the Sun and Earth. The European Space Agency and NASA distribute observing alerts, urging teams to collect new data whenever visibility conditions are favorable. Their shared priority is straightforward: document the physics driving the comet's activity. That includes determining how much material is escaping from the nucleus, identifying which ices vaporize most strongly, measuring dust grain sizes, and calculating any subtle deviations in the comet's course caused by non-gravitational forces, slight accelerations produced by jets of outgassing gas. Spectroscopy plays a central role in this scientific effort. By breaking down the comet's light into its component wavelengths, astronomers can identify which molecules are present, from water vapor to carbon monoxide and carbon dioxide. Because different substances sublimate at different temperatures, each chemical signature helps scientists determine how the comet's interior responds to sunlight. The detection of carbon dioxide, for example, is especially significant. As CO becomes active at much lower temperatures than water ice, CO-driven activity dominates. It would imply that some regions of 3I Atlas hold volatile reservoirs capable of erupting far from the Sun. That possibility aligns with a handful of recent observations, suggesting intermittent jet-like bursts, events that observers often describe with terms like cryovolcanic jets or ice vents. Yet scientists emphasize caution. While jets are entirely plausible, many features that appear exotic can emerge from far more ordinary cometary processes. Dust moving along slightly different trajectories, sunlight pushing fine grains outward, or the angle at which Earth views the coma can create structures that look anomalous even though they come from standard physics. This is precisely why Hubble's geometric perspective, combined with repeated imaging from different angles, is so essential. Real structures persist across viewpoints, while projection effects shift or vanish. Amateur astronomers also contribute to this global effort. though most cannot match the sensitivity of professional systems. Enthusiasts with medium-sized telescopes provide dense time series records, nightly measurements that fill observational gaps left by large observatories with limited scheduling windows. With an 8-inch or larger telescope and a cooled camera, observers can capture monitorable changes in brightness or asymmetry. These contributions, though humble, enable a richer picture of the comet's evolution, complementing high-end space-based images. A surge of public interest followed reports of jet-like behavior, with some commentators speculating about extraordinary interpretations. A small subset even proposed technological or artificial origins, theories that circulate whenever an interstellar object displays unexpected features. But the scientific community maintains a consistent principle: extraordinary claims demand extraordinary evidence. To even consider a technological explanation, researchers would require multiple independent observations across several wavelengths, processed by different instruments and teams, all showing features that cannot be produced by any natural process. At present, no such data exists. The features observed so far: asymmetric coma, faint sunward extension, intermittent brightness fluctuations, all fall squarely within the range of natural cometary behavior, especially for an object entering the inner solar system for the first time. The debate about jets, fragments, or dust morphology ultimately hinges on data from three primary sources: imaging, spectroscopy, and astrometry. Imaging reveals shape and brightness structure. Spectroscopy identifies chemical composition. Astrometry tracks position with extreme precision, detecting subtle trajectory shifts that outgassing might cause. When these data sets align, for example, when strong CO signatures appear simultaneously with visible jets, or when a tiny acceleration matches a period of increased brightness, scientists gain confidence in their interpretation. Without this triangulation, any single image or measurement remains ambiguous. The Hubble image from November 30th demonstrates the importance of repeatability. Much like a baseline medical scan, it gives researchers a reference for comparing future changes. If the sunward extension grows, sharpens, or shifts with time, that evolution will point toward specific mechanisms. If it fades or appears inconsistent across wavelengths, it may reveal itself as a projection effect rather than a physical structure. These distinctions can only be made through systematic follow-up imaging at multiple phase angles, spectroscopy at different heliocentric distances, and astrometry taken under stable, well-calibrated conditions. For those watching 3i Atlas casually or creating content about it, the best source of reliable updates remains the institutional feeds from NASA, ESA, and major observatories. Each release includes timestamps, instrument specifications, and raw or lightly processed images. These sources avoid speculation, instead presenting measurable quantities that viewers can verify. In contrast, many sensational claims rely on low resolution or over-processed images that obscure more than they reveal. When one compares a noisy amateur frame to a professionally processed Hubble image, the difference between ambiguity and clear scientific information becomes obvious. As 3i ATLAS continues on its outbound journey, most observers should temper expectations. The comet remains relatively faint, never approaching naked eye visibility. Those attempting to image it will require patience, steady tracking, and long exposures. But whether viewed from a backyard telescope or a billion-dollar space observatory, each measurement feeds into the same unfolding narrative: understanding the composition and behavior of one of the rare interstellar visitors passing through our cosmic neighborhood.